permeability. Thank you. So the thing is, do you remember permittivity of free space was related to, was this constant epsilon 0 that kept coming up over and over again in electricity? What you will see throughout this course now is that in magnetism, we will always encounter this constant called mu 0, which is the permeability of free space. Okay? So this constant is going to be, this is a fundamental constant, you know, of the universe, just like speed of light is in the vacuum is 3 times 10 power 8 meters per second. It's constant, fundamental constant. Similarly, this is a fundamental constant. Now, notice what we have here. So first thing that you notice is that the magnetic field produced by this little current element here is going to be large if the current is large, right? And it goes inverse square of the distance. So the farther you go from this point, the magnetic field gets weaker and weaker due to this dl. How much weaker? It goes as 1 over r square. This r hat is the unit vector, right? Can you tell me the direction of the magnetic field, dB? You can use your right hand rule. It's dl cross r hat, right? Huh? How would you do it? Huh? So put your fingers in the direction. First of all, again, the magnetic field will be perpendicular to dl and it will be perpendicular to r hat, right? But the thing is, what you have to do is use your right hand rule, right hand screw rule for cross products. Put your fingers in the direction of dl, cross it in the direction of r hat, and do you see my thumb is going in? So that would be the direction of dB. So over here, dB is pointing into the board. Is everybody with me? Now if you want to find the magnetic field due to the whole wire, what do you have to do? Do you have to do an integral? Yeah, add up the contribution to magnetic field due to all of these dLs. But notice you're not adding a scalar quantity. dl cross r hat is itself a vector. So the magnetic field due to the whole wire will be integral dB, which will be integral mu 0 over 4 pi I dl cross r hat divided by r square. By the way, this is what's called Biot Savart Law. Is this, do you see that this integral is not going to be easy? Because again, what you have to do, if you told me that the magnetic force is pointing into the board here, you have to find now contribution due to this dl at this point, 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 using this law for all of those little dl's and add them up. That's what this integral is. It's really a sum over all the little dBs that you have calculated, the contribution due to this little current element at this point, due to this little current element, what is the magnetic field produced, due to what, this, etc., and add them up. That's what this is. This typically will not be an easy thing to do. I'm going to move on to talking about Ampere's law. And Ampere's law is only going to give you the magnetic field if you have a very high symmetry in your current distribution. Can you think of a case where you have very high symmetry in the current distribution? Huh? Yeah, for example, a very long straight wire, a long thing you can think is almost infinitely long. That has a very high symmetry. So you will see that instead of doing some crazy integrals here, like, because if I had a very long straight wire carrying current, in order to do this integral, I'll have to integrate this thing from minus infinity to plus infinity. If this thing went from, let's say this is minus infinity and that, kept going up to plus infinity, even this integral is not going to be an easy thing to do, even for that case, right? Although we can do it. But you will see using Ampere's law, our life will become so easy, just like using Gauss's law, our life became really easy when we wanted to calculate the electric field. So I am going to move on to Ampere's law now. At least you have a gist of how to do it using Biot Savart law, which is, you know, the more complicated way of doing things. This is like Coulomb's law. The only problem is that this one is more like Coulomb's law in the sense analog of Coulomb's law, right? Because it tells you the magnetic field due to a small current element. This is the superposition principle. We are saying the whole magnetic field will be integral. So since it's complicated and we are not going to spend too much time on this, let's move on to the equivalent of Gauss's law that helps us find the magnetic field due to highly symmetric current distribution. And using that, we are going to find the magnetic field produced by an infinitely long current carrying wire. We are going to find the magnetic field produced by what is called a solenoid or coils of wire which are very closely wound together. If this thing was infinitely long, this is the kind of thing you use an MRI machine. For example, you get shoved into one of these things, solenoid or coil. We will find magnetic field due to what is called a toroid. If you take a long solenoid and you kind of wind it around at the end, it will become like a donut, right? That is called a toroid. All of these systems have a lot of symmetry, and we should be able to just flip our fingers and be able to find the magnetic field due to these current distributions using Ampere's law. So let me teach you Ampere's law. All right. Any questions so far? All right. So Ampere's law. So this is analogous to Gauss's law for electricity. Okay, so Ampere's law says this. It says integral over any closed loop of B dot dl is equal to mu 0 times the current enclosed. Notice that there are some differences between Ampere's law and Gauss's law. Remember, Gauss's law was this. Recall, Gauss's law was integral E dot dA over any closed surface was Q enclosed over epsilon 0. So the first difference that you find is what? Here you have electric field in Gauss's law. In Ampere's law you have magnetic field. But one huge difference is that here we have integral E dot dA over a closed loop. What was integral dA over a closed loop? That was a surface integral, right? Over a closed surface. That is not the case for Ampere's law. Ampere's law, this dl is what is called a line integral. It's not an area or surface integral, it's a line integral. So you're basically integrating over any thread, closed loop. It's not a surface integral, it's just a line integral. And when I say it's a closed line, I mean you have to take, say for example, take a thread, you can move it around as much as you like in whatever direction, but it must end at the same point. That's what I mean by saying it's a closed loop. And these loops are again imaginary loops, just like these closed surfaces could be imaginary surfaces. We used to call these surfaces Gaussian surfaces. We will call these closed loops Amperian loop, because Ampere was the one who came up with this law. Okay, so these are going to be tricks for us to find the magnetic field, because look, you can see the formula right now is not directly telling us magnetic field. What is it telling us? It's telling us what is B dot dl over a closed loop. The only time this, and this is equal to mu 0, that constant, just like epsilon 0 here. And here we had charge enclosed in this surface, and here we have current enclosed in this loop, this imaginary loop. Now notice, this law is going to be helpful for us to find the magnetic field only if we can cleverly choose this Amperian loop, this thread, to be such that we can claim at every point on this loop the magnetic field due to this current distribution better be the same, the magnitude of magnetic field, because then we can pull the B out, and as soon as we pull the B out, if we are able to pull this B out, what will be integral dl? Huh? Integral dl will just be the perimeter of the loop, wouldn't it? So for example, if it was a circle, it will be 2 pi r. It will just be whatever is the perimeter. Just like here, if you remember, the only time Gauss's law was useful for us was when we were able to choose these closed Gaussian surfaces in a clever way, such that we could say, hey, electric field magnitude is constant, let's pull it out, and integral dA just turned into the area of that imaginary surface, the Gaussian surface, right? And just like in the case, you always drew your Gaussian surface to include the point where you were interested in finding your electric field, remember? Here, we should always choose our Amperian loop to include the point where we are trying to find the magnetic field. So for example, if you are interested in finding what is the magnetic field here due to this current, you know, I should choose a loop. I should choose an Amperian loop which includes this point, right? Do you see what I'm saying? If I'm interested in finding what is the magnetic field at a distance r away from this current carrying wire, I should include the point where I'm interested in my Amperian loop. But of course, I cannot choose any silly Amperian loop and be able to say, well, from the symmetry of the situation, the magnetic field magnitude is the same. I have to make sure that the magnetic field magnitude is really the same at every point on this loop, because then this B can be pulled out, the magnitude of B can be pulled out, and integral dl is simple. Then it's just the perimeter. Is the idea clear? Now, of course, Ampere's law is more general than this. Let me first explain to you, what is the meaning of I enclosed? Because, so let's choose a crazy looking loop, let's say it like this. This is my closed loop, Amperian loop, right? Any closed thread will be a closed loop. This thing tells you closed loop. Let's say that I have a current carrying wire that is carrying current into the loop, which has a magnitude of say 2 amps. This is I1. I have another one over here which is carrying current out, and this is, let's call it I2, which is 1 ampere. The question is, how much is the current enclosed? First of all, since you have a loop now, do you see you have a loop now? You have the choice of saying, oh, I am going to consider this line integral either this way, either in the counterclockwise direction or in the clockwise direction. So you can go through dl, you can say, oh, my dl, your dl's are this, little infinitesimal length elements here, dl, 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 dl. So this whole loop can be broken. This is your imaginary Amperian loop. You've broken it into little dl's, and the point is, you can choose a clockwise or counterclockwise direction or clockwise direction for traversing it. Here, I chose it to be counterclockwise, right? Now, how do you figure out, once you've chosen a direction for which way you traverse the loop, the Amperian loop, this imaginary loop, you have to decide what current is positive and what current is negative. It turns out, if you use your right hand and you put it in the roughly in the, pointing in the direction of the way you are going to traverse the loop like this, anything that points in the direction of your thumb, call that current positive, the other current will be negative. So in this case, this 1 amp current will be positive, this 2 amp current will be negative, the way I traverse this loop. Does everybody understand that? Just put your fingers like this. Oh, my thumb is pointing this way. Let me consider I2 to be positive current and I1 will be negative. So what will be I enclosed here then? Huh? Negative 1 amp plus 2 amp, sorry, plus 1 amp minus 2 amp, which is equal to minus 1 amp. Is everybody seeing that? How to figure out current enclosed? Okay, let me give you a question just to make sure that you really understand what we are talking about. So, and notice that Ampere's law works for any crazy looking loop like the one that I drew. Of course, this won't be the most useful loop to choose for any problem in which we really are interested in finding the magnetic field. Because in those problems, there's got to be symmetry, and you need to choose our loops in a symmetric manner also, right? In order to say that the magnetic field is constant everywhere, for example. So, okay, tell me about this loop. So here is a loop. I have this is a cross. This is a current that's 3 amp that's going in. This is a dot which is 2 amp. this is another dot which is 1 amp, and then I have here another current, let's call it I1, I2, I3. This is I4, which is across here, which is 5 amps. Let's decide to traverse this loop in the counterclockwise direction. The question I have is, when I do this thing, integral B dot dl, tell me what is the current enclosed. Everybody should be talking to a person next to them. You have half a minute. All right, somebody from the third row, please. Anybody from the third row? What is the current enclosed? Huh? Anybody from the third row? 0. The current enclosed here is 0, because first of all, this thing is not inside the loop, right? That's outside the loop, because this is my loop. And again, if I put all the fingers in my right hand in the direction of the current, our convention, this is like a convention. This is not going to kill you if you don't choose this convention, because this is just so that we are all consistent. We have decided to call these two positive currents. So we have positive current equal to 2 plus 1, 3 amperes current is enclosed, which is positive, and there is also minus 3 amperes that is not positive, that's negative. So the total current enclosed will be 0. Is everybody with me? So that means what we see here is that integral B dot dl is equal to 0 in this case. Is that making sense? Okay. Now what about, by the way, just because integral B dot dl is 0, does it mean that the magnetic field at every point here is 0? No. In fact, I cannot infer anything about magnetic field. Why? Because look, integral B dot dl is this. Magnitude of magnetic field, magnitude of dl times cosine of the angle between the magnetic field and dl, right? It's possible. So basically, for example, here, if you look here, your dl is always tangent to this circle here, so dl is like this, tangent to the circle. But magnetic field here could be, say, this way, or it could have, so in some places it's possible that dl and magnetic field are making an acute angle, and in some cases they are making obtuse angles, such that cosine of something greater than 90 is negative and cosine of something less than 90 is positive. So what you could have is that, say, the contribution to this integral B dot dl from, say, this might turn out to be, say, positive, and from here might turn out to be negative, such that the total turns out to be 0. All this is saying is that integral B dot dl is 0. It's not saying magnetic field is 0 at every point on that loop. Those kinds of conclusions you're not able to make unless you can assert that from some symmetry in the problem you can pull out the magnetic field. If the magnetic field is out of the loop, out of that integral, and then you are getting a 0 on the other side, then yes, you can say, that circumference is not going to be 0, and so then the magnetic field itself is 0, but not in this case. Is everybody convinced that here it means nothing in terms of what the magnetic field magnitude is at different points, right? Now let us do a problem that does have symmetry. For example, an infinitely long straight current carrying wire. Let's try to use this Ampere's law to find the magnetic field produced by the current carrying wire, say at a distance r away. Okay? So the wire could look like this. This is an infinite. This is carrying current I. Okay, so this is an infinitely long straight wire and this is carrying current. Okay, somehow we want to be able to use Ampere's law, which says integral B dot dl over any closed loop is equal to mu 0 times the current enclosed. I want each and every one of you to talk to a person next to you, because this time I really will try to pick one person, and I'll ask, you know, what kind of loop should I choose so that I can guarantee that the magnetic field magnitude is constant at every point on that loop due to this current carrying wire. Is the question clear? Because it's up to us, just like in Gauss's law, choosing a Gaussian surface, those imaginary surfaces were up to us. So here we are asked, you know, we are asked this question: find the magnetic field here at a distance r away from this wire. The question is, what kind of a loop, you know, what kind of a thread should we choose such that we can actually make our life easy and guarantee that yes, magnetic field magnitude due to this wire better be constant at every point on this loop, because that will help us pull out the magnetic field magnitude, right? Talk to a person next to you, please, everybody. All right, somebody from the front row here. Anybody from the front row here? What would be a good loop to choose? Go ahead, folks. It's a friendly class. Any good loops to choose? So I have an infinitely long straight wire. I'm asked to find the magnetic field at a distance r away right here due to the current that is flowing in this wire, and I want to be able to use Ampere's law to find the magnetic field at this point due to the current in this wire. What loop should I choose? Anybody? Okay, okay, here we are not choosing surfaces, we are choosing circles. So we are choosing, can I choose a circle around the wire? How many people agree with him? Okay, he is absolutely correct. What we should choose here is basically we should choose a thread which is circling around this wire, right, with the wire at the center. And notice now we are not talking about surfaces. This is not going to be a sphere or a cylinder or a you know, those kinds of things. This is going to be really literally a thread. So we are talking about circles here. So I think his idea is an excellent one. We should choose our imaginary surface, sorry, imaginary thread, imaginary loop to be a circle that is passing through this point where we want to find the magnetic field, and that is centered at the current. The front view of this thing will look, the top view will look like this. Let's say that the current carrying wire was pointing at you like this, at infinite current carrying wire. Basically, and suppose you ask me what is the magnetic field here at a distance r away from it. Basically, we can choose, our Amperian loop, our imaginary loop. Isn't this a horrible circle? Okay, I don't think I did a very good job of this circle. Anyway, the point is, this wire should be at the center. I'm just drawing two perspectives of the same thing. Now in this case, will you be able to argue with your friend and convince them? Tell me how many of you think that you can definitely convince your friend that the magnitude of magnetic field produced by this infinitely long wire at every single point of this circle will be the same? Nobody? Two people only? Wouldn't you say from the symmetry that there is nothing preferable about this point, this point, this point, this point, this point? All of these points have exactly the same symmetry with respect to this infinitely long wire, right? So if the magnitude here you found is 0.25 Tesla, it better be 0.25 Tesla, 0.25 Tesla due to this current everywhere. Wouldn't you be able to convince everybody? Okay, so if that's the case, let's use this Ampere's law. Ampere's law says this: B dl times cosine theta is equal to mu 0 times I enclosed. So one thing we are saying is that if we choose this loop, we are sure that B is a constant, the magnitude of magnetic field is a constant, we can pull it out, right? Also, just like in the case of Gauss's law, we need to be able to figure out what is the direction of magnetic field even before we have done anything related to Ampere's law to find the magnetic field. It turns out if you do experiments, you know what you'll find, and I'll show you next time. Next time I'll show you these experiments. They're very nice. They show you if you do experiments to figure out which way the magnetic field is due to the current carrying wire. Do you know which way it points? One easy way to do the experiment will be take a very long straight current carrying wire, right? Put compass needles around it and see which way the compass needle gets oriented. And you know what you'll see? It gets oriented in circles. So in other words, what you will find is that the magnetic field produced by the current carrying wire actually forms circles around the wire. So magnetic field here, for example, will be a circle here. These are going to be closed circles. And in fact, the magnetic field, the magnitude of magnetic field produced by the current carrying wire is what we are going to find using Ampere's law. So the direction of magnetic field form circles around the wire. This is how experiments, this is what experiments show. I'm going to show you next time. They show that the direction of magnetic field forms circles around the wire and this is given by right hand rule 2. Right hand rule 2. Or you can call it, if you want, you can also call it right hand thumb rule. What is this right hand thumb rule? Basically what it says is that put your thumb, because you need to know if the magnetic field, if this is a very long straight wire and we are already saying that the magnetic field due to it is forming circles, you know, concentric circles around the wire, we need to know, is it like clockwise circles, clockwise or counterclockwise? Use your right hand rule 2 or right hand thumb rule. What it says, if you put your thumb in the direction of current of your right hand, thumb of the right hand, your fingers will curl around in the direction in which the magnetic field due to the wire points. Does that make sense? No? Okay. So for example, let's say that this wire is carrying current up. If this wire is carrying current up, I put my thumb in the direction of current. Do you see all my fingers are curling like this? So that means the current, the magnetic field that is produced by this wire is forming closed loops like this in the counterclockwise direction as opposed to clockwise. If the current was down, then the magnetic field will be forming circles like this, because we are really talking about, so let's talk about this picture here. If the current is coming out at you, right, and I'm saying find the magnetic field here at some distance r away, it could be either like this or it could be like this, right, clockwise or counterclockwise. Use your right hand thumb rule. Put your thumb in the direction of current. Do you see my fingers are curling like this in my right hand? And that says that the magnetic field produced by this current is actually pointing in the counterclockwise direction. Does that make sense? Okay, what about over here? The magnetic field at some distance r2 away, again, you know, same thing. Put your thumb in the direction of current. You see your fingers are curling like this. Everybody should be doing it with their own hand. You never get an idea about this unless you do it yourself. Do you see what is the magnetic field here? Again the same thing. The magnetic field at some distance, you know, r away, you can find in the same way. Use your right hand thumb rule this time. So there are only 2 right hand rules. I don't want you to remember 500 right hand rules, you know, which might be in 500 different books, because every book has a different way of doing things. I want you to only remember 2 different right hand rules. One is the right hand rule for cross products, right, or screw rule. That's what we were doing earlier. So for example, if you have F is equal to QV cross B, or that is the force on a moving charge in a magnetic field, or if you have F is equal to I L cross B, which is force on a current carrying wire in magnetic field, both those will be exactly the same right hand rule. Put your all fingers in the right hand in the direction of the first vector, curl it in the direction of the second vector, and the third vector, which is the cross product of the two, will be pointing in the direction of your thumb, right? Even before you have figured out this, you should actually think about a plane in which the first 2 vectors lie, for example V and B, and you can narrow the direction to 2 and then see which way the thumb points. That's right hand rule 1 if you like, or that's the right hand screw rule, or right hand rule of cross product. This is the only other right hand rule you'll see in this course. This is called right hand thumb rule, and this is for finding magnetic field, which says if you put your thumb in the direction of magnetic field, your fingers of the right hand will curl around in the direction of magnetic field. Did I say put your thumb in the direction of current or not? Put your thumb in the direction of current, your fingers in the right hand will curl around in the direction of magnetic field. Does that make sense? So tell me, based upon that, does that make sense that if the current was flowing up, these circles will be like this? The magnetic field. By the way, the magnetic field at any point will be given by the tangent to the circle. If you ask me what is the direction of magnetic field here, it's the tangent to the circle here. What is the direction of magnetic field here? It's the tangent to the circle here. What is the direction of magnetic field here? It's the tangent to the circle here, etc. Right? Is that making sense? So for example, if you are, in this particular case, if the current is coming out, the magnetic field using this right hand rule 2 or thumb rule, it's pointing like this. If you ask me what is the magnetic field here due to this current, it's tangent to the circle here, here it's tangent to the circle here, here it's tangent to the circle here, etc. Right? All right. So what can we do with Ampere's law then? Ampere's law helps us find the magnitude of magnetic field, just like Gauss's law helped us find the magnitude of electric field. Remember, for cases where there were symmetries. So let's use Ampere's law. Is everybody convinced I can pull the B out of this integral? Let me not make this picture look complicated. So here is my Amperian loop. I already know the magnetic field lines form closed circles around it. This is what experiments have shown. And so now the question that I have is, what is the magnitude of magnetic field at every point here? That's what we are trying to do using Ampere's law. All right? So everybody with me, that if I choose my Amperian loop cleverly such that it is forming a circle with the wire at the center, I can pull the B out because it's the same. Okay, so let's pull B out. Also notice, there's another thing that we can notice. What about cosine theta? If the magnetic field is forming closed circles, what is the direction of dl? dl is also always tangent to the loop, because isn't this also the dl? You know, little dl's. Here dl is going to be tangent here, here dl is tangent here, here dl is tangent to the circle here, tangent to the circle here, etc. So do you see that at every point the direction of dl, so here for example the direction of dl is tangent to the circle, the direction of magnetic field is tangent to the circle. So do you see the angle between dl and the magnetic field is 0? They're both pointing in the same direction. So basically what we have then is, this is cosine 0, and cosine 0 is 1. Okay, so this is equal to mu 0. And how much is the current enclosed? Is the whole current enclosed? Yeah, the whole wire is inside. So the current enclosed is I. Cosine 0 is just 1. So what we have here then is B dl over the closed loop is equal to mu 0 times I. What is integral dl over the closed loop? See, we chose it to be a circle, right? The circumference of a circle is? Very good, it's 2 pi r. So basically we have B times 2 pi r is equal to mu 0 times the current, and hey, we have it. B is equal to mu 0 I divided by 2 pi r. So now we know everything that there is to know. We know that the direction of magnetic field is given by the right hand thumb rule like this, and we know that the magnitude of magnetic field at this point is given by this. B is equal to mu 0 I divided by 2 pi r. Okay, suppose let's say I was equal to 0.5 amps, and let's say that the distance was 1 meter. What would be the magnetic field? Can we do it? So let's try an example. B in that case will be mu 0, and mu 0, remember, is 4 pi times 10 power minus 7 Tesla meter per ampere. That's the SI unit of mu 0. Current we have been given is 0.5 ampere. So this would be 0.5 ampere divided by 2 pi times r, and r is given to us to be 1 meter. So this is going to be the magnetic field. Pi and pi get cancelled. We are left with 2 times 0.5 is 1. So 10 power minus 7 Tesla. Very weak magnetic field. Right? So if you have, notice this, if you have 0.5 ampere current, the magnetic field at 1 meter distance away is extremely weak. It's 10 power minus 7 Tesla. Right? Is that making sense? Any questions about this? Anybody? Do you think we can find the magnetic field due to some other cases? For example, how about like 2 wires? If we have 2 long straight current carrying wires, can we use this magnetic field plus superposition principle to find the net magnetic field? We can, right? Let's try it. So suppose I gave you a question in the exam, and this kind of question I always give actually. Suppose you have one wire like this. This is carrying current I1, which is say 1 ampere. There's another wire here, I2, which is carrying current, let's say 2 ampere, or let's say this is also carrying current 1 ampere. The question is, what is the magnetic field, say, at the center? Let's say this whole distance is 2 meters. So one question is, what is the magnetic field at the center here? B is equal to what? The other question is, what is the magnetic field here, say at a distance of 0.5 meter to the right of this wire? And when I say what is the magnetic field, remember, magnetic field is a vector quantity. It has both magnitude and direction. So first, what do you think we could do? Do you think that the magnetic field at this point is produced by both wires? It is, right? Similarly, magnetic field at this point is produced by this wire plus this wire. So hey, and we know how to find magnetic field due to each of these wires. Due to each of these wires, this is the magnitude of magnetic field, right? The direction of magnetic field is given by the right hand thumb rule, right? So then is it easy to find the net magnetic field? It's not hard, right? Because we can use superposition principle, couldn't we? Okay, but in order to do that, the way this wire is drawn, I think it will be a good idea for us to actually think about. So in this plane, if you use the right hand thumb rule, what would you say is the direction of magnetic field produced by this wire that is carrying current 1 amp? Huh? Very good. Do you see that it is clockwise? Because if you put your thumb in the direction of the current, my fingers curl like this. Do you see the current is, the magnetic field is going clockwise? Is everybody convinced magnetic field is clockwise? Sorry. Thank you. I repeated what they said. That's good. So the thing is, the magnetic field is counterclockwise. I'm sorry. Is that making sense? So the magnetic field is going counterclockwise. Sorry about that. And if the magnetic field is counterclockwise, what would be the magnetic field here, in the plane in which these 2 wires lie? Remember, magnetic field at any point on that circle is going to be tangent to the circle, right? So notice, if this is a current carrying wire and we are saying, oh, the wire is carrying current that way, the magnetic field is forming these circles. If I ask you what is the magnetic field here, you draw a tangent and you say it's like this. If I ask you what is it here, you draw a tangent and you say it's like this, right? If I ask you what is it here, you draw a tangent and you say it's like this. So in the plane of the two wires, does everybody see that over there, if it's counterclockwise, the magnetic field is actually pointing into the board? Is everybody convinced that, you know, if we call this wire 1 and wire 2, is everybody convinced that over here B1 is pointing into the board because it's like this? Right? Do it with your hand. It's really forming closed circles, but I'm only interested in one point in that circle. Okay, what about you to this one? Yeah, see, use your right hand thumb rule again. Put your thumb in the direction of current. Does everybody see that magnetic field lines due to this wire 2 will form closed loops such that on this side it's pointing in the plane of this board, and on that side it's pointing out, right? So does everybody see that over here B2 is a dot? Okay, so let's figure out what is B net then. What will be B net? B net, first of all, is going to be, let's say that, you know, out is positive. This is my convention. You don't have to choose it, but you clearly should say what is positive for you and what is negative for you. So if out is positive for me, then I'm going to say B net is B2, which is out, minus B1. Is everybody seeing why I'm choosing the negative sign between the two? Because B2 is positive, it's coming out, and B1 is in the negative direction that I chose as my convention, right? By the way, so now what is this going to be? This is going to be mu 0 times I2 over R2 minus mu 0 times I1 divided by R1. But in the problem that we have been given, look, I1 is equal to I2. Isn't it? Both of them are 1 amp. And is R1 equal to R2? No, notice that this is going to be my R1 and this is going to be my R2. Those distances are equal because this point is in the middle and each of them is like 1 meter. So basically what we have, this is equal to 0. Since I1 is equal to I2 and R1 is equal to R2. Is everybody with me? Let's try to do the problem over there. Okay. Who wants to tell me what would be the direction of magnetic field here due to this wire? 4th row, please. Somebody from the 4th row. What would be the direction of magnetic field at this point produced by this wire? Huh? Anybody from the 4th row, please? Into the board? Is everybody convinced this is into the board? See, because it's forming closed circles and at this point the tangent will be pointing into the board, right? So we know, for example, now that B2 at this point is into the board. Okay, somebody from the 5th row, what is the direction of magnetic field at this point produced by this wire? Huh? This wire is also carrying current up. What would be the direction? Go ahead, please. Huh? Go ahead. Into the board also, because look, if this is my thumb, using the right hand thumb rule, any point on this side of the wire, the point is every point on that side of the wire in the plane of the board will have magnetic field going in due to this wire and magnetic field going out on this side. Does that make sense? It depends upon whether you're to the left or right. So we know that B1 is also across. So that means B net at this point for part B will be both crosses and both of them are negative. So it's minus B1 minus B2, which is equal to minus mu 0 times I divided by 2 pi R1 prime minus mu 0 times I divided by 2 pi R2 prime. Okay, just give me a second. Who wants to tell me, by the way, I's are the same. Each of them is 1 amp. What is R1 prime? It's this distance, right? Which is what? Very good. It's 2.5 meters. What is R2 prime? Just 0.5 meters. So use both R1 prime and R2 prime. Each of the currents is 1 amp. You can figure out what would be the magnetic field in Tesla, right? And notice you have to add both of them. The total thing will be very negative number. And what does the negative number mean for you? That the magnetic field is pointing which way? The net magnetic field is into the board, right? Because that's what I chose to be positive. Have a wonderful day, folks.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.